So, electrolytic conductance is the today's topic. So, first of all we should define what is an electrolyte. Electrolyte is a substance which when dissolved in water gives ions. For example, if you take NaCl, dissolve it in water, it dissolves in water and gives Na plus ions, Cl minus ions. So, this is called an electrolyte, and this in aqueous solution act as an electrolyte. For example, I want to define a non-electrolyte. What is a non-electrolyte? Non-electrolyte is one which also dissolves in water but does not produce ions. For example, when you add urea to water, it will dissolve in water and will produce urea molecules, and these urea molecules do not carry any charge. So, this is dissolved urea, this is crystalline urea. So, this is soluble, but it does not produce ions. So, we call this as non-electrolyte, whereas NaCl we call it as electrolyte. Both electrolytes, non-electrolytes, soluble in water, but electrolyte produces ions, non-electrolyte does not produce ions. That is the thing. So, what is an electrolyte? Produces ions, and these ions will conduct current when subjected to electrolysis. Na plus ions and Cl minus ions conduct current. So, that is what we call electrolytes. So, these electrolytes can be defined into two types. Electrolytes are two types: strong electrolyte and weak electrolytes. What is a strong and what is a weak electrolyte? Strong electrolyte, weak electrolyte. For example, I am adding HCl, an acid, to water, and this HCl, when 100 molecules of HCl is added to water, it almost undergo 100% ionization. So, you may get almost 100% H plus and 100% Cl minus ions. We call it as strong electrolyte. A weak electrolyte is, for example, if you take HCN, that is also an acid. When you add 100 molecules of this, you will get H plus ions and Cn minus ions, but these H plus ions are say some 20% and these cyanide ions are also only 20%. The remaining 80% of HCN did not dissociate, but is in dissolved condition only. So, that is undissociated acid, but it is a dissolved acid. So, this will be called as a weak electrolyte and this is called as strong electrolyte. So, finally, strong electrolyte undergoes maximum ionization, weak electrolyte undergo lesser degree of ionization, that is called degree of ionization. So, what is the factors influencing the electrolytic conductance we will study now. So, in this electrolytic conductance we should learn some terms like resistance. What is resistance offered by an electrolyte? Resistance offered by an electrolyte. For example, I am taking an electrolyte having A plus B minus ions. This is an electrolyte, and I am keeping two electrode plates in the electrolyte. Two electrode plates I put. Now, the ions are between the electrode plates. So, these when subjected to electrolysis will migrate towards oppositely charged electrodes. Due to their motion, they experience some resistance, and the resistance experienced by the electrolyte is directly proportional to the distance between the electrode plates. Distance between the electrode plates. So, more is the distance between the electrode plates, more is the resistance experienced by the ions. A plus migration, B minus migration is very much suppressed due to larger separation between the electrodes, and the resistance experienced by the electrolyte ions when they conduct current is inversely proportional to area of cross section. Area of cross section means this one. So, the plate, surface area of the plate also decides electrolytic conductance. Resistance is directly proportional, inversely proportional to area of cross section. More is the area of cross section, resistance is minimum. With that larger surface area, the conductance is little enhanced. So, resistance is inversely proportional to area of cross section. Altogether we can say R is inversely proportional to, or R is proportional to L by A, removing the proportionality by keeping a constant rho into L by A. What is rho here? Rho is called specific conductance, specific resistance. Rho is called specific resistance, or we call it as resistivity. Resistivity. What do you mean by resistivity? Resistivity. For example, if you take an electrolyte and in this solution I am taking 1 cc of the solution, just 1 cc means 1 ml, and how many ever ions are there in that? All the ions will experience some resistance. The resistance experienced by these ions is called resistivity. Resistance experienced by all these ions in 1 cc is called resistivity or specific resistance. Suppose if you modify this reaction, this equation, R by rho is equal to L by A. What is 1 by rho? We can take it as K. So, R into K. K is called specific conductance. Specific conductance, or it is also called conductivity. This R into K will be equal to L by A. This L by A is called cell constant. Why it is called cell constant? When you take any cell, this is closed one, the electrodes are welded here at the fixed places. So, the distance between the two electrodes you cannot alter. At the same time, the area of cross section of the electrode plate also is fixed. So, area of cross section is fixed, as well as the distance between them is also fixed. Both are fixed for an electrolyte, for an electrolytic cell. So, this L by A is called cell constant, and is represented as G star, cell constant. In this conductivity cell, you can alter any electrolyte, but you cannot alter the distance between the electrodes as well as the area of cross section. L fixed, A fixed, only thing the solution or the electrolyte in this conductivity cell only you can change. That is why we call it as cell constant. Cell constant is nothing but L by A, which is nothing but resistance into specific conductance. What is molar conductance? When you take some volume of solution, V volume of solution, any amount of solution you can take, and you add 1 mole of solute in that, 1 mole of solute, that is an electrolyte. So, it will give some A plus and B minus ions. The conductivity shown by all these ions, that is 1 mole of solute present in VCC of solution, that is called molar conductance, and we can calculate the molar conductance as 1000 into K by molarity. What is K here? K is nothing but specific conductance. What is specific conductance? Suppose if you take 1 cc of solution, 1 cc of the solution, and all the ions present in this, whatever the conductance shown by them is called conductivity. Conductance shown by all the ions in this 1 cc is called conductivity, or we call it as specific conductance, we call it as K. Then overall conductance is K into VCC. So, we write it as molar conductance is specific conductance due to 1 cc as well as the total volume, that is nothing but V in cc, V in cc, that is what altogether molar conductance. Then what is equivalent conductance? Equivalent conductance is defined as, take some VCC of solution, VCC, and add 1 equivalent of solute, just 1 equivalent of solute you add, 1 equivalent of solute, and that also will give ions. The conductivity shown by all these ions, that is 1 equivalent of electrolyte in VCC of solution, that is called equivalent conductance. It can be calculated as 1000 K by normality. Normality is the concentration of this solution. Instead, 1 cc will show certain conductance. 1 cc will show certain conductance. We call it as what? Specific conductance. This specific conductance, and there are VCC. This is for 1 cc, there is VCC of solution. Altogether, equivalent conductance is conductance due to 1 cc into total volume of solution. Total volume of solution in cc containing 1 equivalent, that is VCC per equivalent. So, this is nothing but 1000 K by normality. This is one more formula, and this is one more formula to calculate molar conductance and equivalent conductance of electrolytes. For example, relationship between molar conductance and equivalent conductance. What is the relation? Which is more, which is less? We should understand. For example, I am taking sulfuric acid. Say 1 mole. 1 mole means 98 grams of sulfuric acid I am adding to water. 98 grams, that is 1 mole, I am adding to water. So, this will produce more number of ions. So, the molar conductivity is more. Whereas, in the same quantity of water, if I take sulfuric acid, that is only one equivalent of sulfuric acid I am adding. 1 equivalent of sulfuric acid means, you know, it is only 49 grams. So, I am adding only 49 grams. Here I have added 98 grams. Here the number of ions are more. Automatically molar conductivity will be more. And here the number of ions are less because we have added only 49 grams. So, number of ions are less. So, therefore, the equivalent conductivity will be less. But there is a strict relationship between them. We can say that molar conductance is greater than that of the equivalent conductance. Molar conductance is greater than equivalent conductance. But what is the relationship between them? So, this is due to 98 grams, this is due to 49 grams. So, you can say molar conductance is definitely more than equivalent conductance, and it is more by 2 times. So, molar conductance of sulfuric acid is 2 times of equivalent conductance of sulfuric acid, because 1 equivalent is 49 grams only. 1 mole means 98 grams. So, this is more conductance, that is lambda m is more than lambda e, that is lambda m 2 times of lambda e. What is 2 here? 2 is multiplying factor. Why did we multiply with 2? Because the N factor or the valency of sulfuric acid, this is a dibasic acid. It has 2 replaceable hydrogens. That is why we keep it as 2. So, molar conductance of any electrolyte is valency times of equivalent conductance. How do we define valency for any acid? It is nothing but number of replaceable hydrogens. So, sulfuric acid is valency, you can say it is 2, for HCl acid 1, and for magnesium or barium hydroxide valency is number of OH groups. So, it is 2. So, what do we can write for this? Molar conductance of barium hydroxide is 2 times of its equivalent conductance we can write. Then how do we write for salt like aluminum sulfate? Al2SO4 taken thrice. This is an electrolyte. When you dissolve Al2SO4 thrice in water, what do you get? The ions we get are aluminum plus 3 ions and sulfate ions. These are the ions we get, Al plus 3 and SO4 minus 2. How many Al plus 3 we get? According to formula, we will get 2. And how many sulfate we get? 3. Altogether 5 ions are produced. Then what is the valency of it? I want to know the relation between molar conductance and equivalent conductance between these two. So, that is understanding valency. How the valency of Al2SO4 thrice is defined? Valency of Al2SO4 thrice, being a salt, its valency is total positive charge or total negative charge. Either of them you should take. total positive charge is how much? 3 and 2, that is 6. That is the total positive charge, and the total negative charge. Total negative charge is also 3 and minus 2, that is also 6. Altogether, we can say valency of aluminum sulphate is 6. So, if it is 6, the molar conductance of aluminum sulphate is how many times of equivalent conductance? It is 6 times of equivalent conductance of aluminum sulphate. So, like this we can relate between molar conductance and equivalent conductances. In this topic, their units are most important. So, numericals deals with the change in the units. Let us see the units. Resistance, you know the units of resistance are ohms, and the reciprocal of resistance, that is called conductance. We call it as conductance, and the reciprocal of resistance, that is ohms, inverse. Ohm inverse is the units, and this ohm inverse we can say in English we can write it as ohm inverse, or otherwise spelling reverse, Mohs also we can say. And in SI units it is nothing but Siemens. Siemens is the unit of conductance, which is reciprocal of resistance. And we have come across cell constant. Cell constant is G star, which is nothing but L by A. What is L? Distance between the plates. We write it as centimeters, and A is the area of cross section of the electrode. We call it as cm square, that is centimeter square. Altogether, the units of cell constant is per centimeter. Now, we have already come across a relation R is equal to rho into L by A. So, from this we can write 1 by rho is equal to 1 by R into L by A. 1 by rho is equal to 1 by R into L by A. Reciprocal of specific resistance is nothing but called conductance. Reciprocal of resistance is called conductance into L by A. So, what are the units of specific conductance? I want to know the units of specific conductance. Rho. Rho is equal to what? Rho is equal to R into A by L. See here, rho is equal to R into A by L. So, R is what? Resistance, which is ohms, A is centimeter square, L is centimeters. Cancelling 1 centimeter, ohm centimeter is the units of specific resistance or resistivity. Specific resistance or resistivity is ohm into centimeters. So, the reciprocal of it is called specific conductance. Reciprocal is nothing but 1 by rho K. K is what? Ohm inverse, centimeter inverse. The reverse of this. Reciprocal of rho is nothing but K, which is nothing but ohm inverse, centimeter inverse. Then we have come across cell constant, already centimeter inverse. Now, molar conductance. What are the units of molar conductance? We write it as 1000 into K by molarity, I said, molarity. So, units of molar conductance. Specific conductance, this is specific conductance. So, its units are ohm inverse, centimeter inverse, and this is molarity. Molarity means moles per liter, moles per liter, and this liter we should write in terms of centimeter cube. So, we can write it as ohm inverse, centimeter inverse, and this liters when comes to numerator, it is again centimeter cube by mole. This is units of molar conductance. Molar conductance, ohm inverse, centimeter cube, moles. So, if you simplify that, molar conductance is ohm inverse centimeter power minus 1 and cube is centimeter square, and the mole is in denominator, that will come to numerator as mole inverse. So, ohm inverse centimeter square, mole inverse is the units of molar conductance. Similarly, equivalent conductance is what? Molar conductance deals with moles per liter or moles, whereas equivalent conductance deals with what? Normality, that is number of equivalents per liter. So, only thing in place of moles you will get equivalents, that is ohm inverse centimeter square equivalent inverse. So, these are the units of molar conductance and equivalent conductance and their respective units. So, units you should be very careful when you do the problem, that is cell constant and this is conductance units, etc. Ohm inverse and centimeters is nothing but specific resistance. The effect of dilution on electrolytic conductance. When you take a strong electrolyte, it is almost 100% dissociated or ionized. So, if you add AB, an electrolyte A plus and B minus, which is a strong electrolyte, means maximum dissociation occurs. There is a little undissociated AB in the solution. Now, if you take a weak electrolyte XY, XY is a weak electrolyte. What is the meaning of weak? It dissociates, but to a lesser extent. The degree of dissociation is less. So, say 10% dissociated. 10% dissociated means it is giving 10x plus 10y minus. The remaining 90 molecules of XY is still undissociated, but in dissolved condition, undissociated. Now, if you see the conductivity of this and this, there is a higher conductance. Conductance is high for a strong electrolyte due to maximum number of ions, and there is lesser number of ions. So, the conductivity is low. And how these conductances are going to change with dilution, we are going to study, and let us put it in the form of a graph. So, if you take conductance along y axis and concentration along x axis or square root of concentration, no problem. Conductance or concentration we are taking along y axis and x axis. Now, you see I took same concentration 100 in 1 liter. So, concentration is same for both. So, both are at same concentration, but strong electrolyte due to maximum number of ions has a higher conductance. Its conductance is high, whereas for the weak electrolyte the conductance is low. Both are at same concentration, but both are not having same conductances. This is low conductance, this is of higher conductance. Now, this point represents weak electrolyte, this point represents strong electrolyte. So, strong has higher conductance. Now, I am diluting. So, I am adding water. By adding water, what happens? Let us see the effect of dilution. I am adding water. Excess water which is been added can do what? Can make the remaining AB also undergo dissociation. Means if you keep on adding water, the remaining 2% will keep on undergoing dissolution. So, the number of ions keep increasing, and at infinite amount of dilution, means infinite amount of water you have added, then this total 2 moles of AB is also said to undergo 100% dissociation. So, that is what we can see. So, due to dilution, what is happening to the number of A plus and B minus? Already 98, and they are going to increase as 98.1, 98.2 or like that, it may maximum reach 100. So, the conductance of this solution also increases, but not greatly. So, with dilution, the conductance of strong electrolyte is slowly increasing, and the maximum difference you can see is only 2%. This is the maximum conductance you can expect to increase. This is 2%. So, there is a gradual increase in conductance, and if you extrapolate that line, extend that line, it will intersect the conductance axis at one point, and that is the maximum conductance you can see from a strong electrolyte, which is called lambda infinity, that is conductance at infinite dilution of a strong electrolyte. Conductance at infinite dilution of a strong electrolyte is maximum, that is here. Whereas, in case of weak electrolyte, if you start adding water, that is dilution, by dilution this remaining XY also start undergoing dissociation, and the scope for its dissociation is still 90%. So, there is a 90% XY that can dissociate. So, you can have a greater dissociation with the amount of water added. As you add water, so and so this XY dissociate great, and automatically the conductance of that weak electrolyte also increases, and that will take a curve of this shape. So, as weak electrolyte is diluted, the conductance is increasing like this. So, for weak electrolytes, you cannot find conductance at infinite dilution. At infinite dilution, what is the conductance of this electrolyte? You cannot find. Reason? You cannot add infinite amount of water, and you cannot find this line intersecting the conductance axis at any point of time, just like strong electrolyte. As strong electrolyte is intersecting, weak electrolyte is not intersecting at all. So, for weak electrolytes, lambda infinity, that is conductance at infinite dilution, it is not possible either by experiments or not by experiments, and not possible by graph also. Either of these two ways we cannot find lambda infinity of a weak electrolyte. Then how to find the lambda infinity of a weak electrolyte? That is given by 𝗂𝗧𝗪 law. So, what is 𝗂𝗧𝗪 law and what is its significance? How do we represent the conductance at infinite dilution of a weak electrolyte is given by 𝗂𝗧𝗪 law. Let us study 𝗂𝗧𝗪 law. So, now let us see 𝗂𝗧𝗪 law of independent migration. Independent migration, keep in mind. So, here now I am taking a strong acid HCl and a weak acid CH3COOH. When you dissolve HCl in water, you will get H plus and Cl minus. When you dissolve acetic acid in water, you will get CH3COO minus and H plus. Of course, this is not completely dissociating and this is completely dissociating. It can be represented like this. HCl gives rise to H plus and Cl minus. This is almost irreversible, almost completion, whereas acetic acid dissociates irreversible, means there is a dynamic equilibrium between dissociated and undissociated. Now, if you see the mobility of H plus ion here, H plus ion, this is a strong acid. Strong acid means what? It is ready to give H plus. After giving H plus, Cl minus is available, and the Cl minus is not having great control over the H plus, because Cl minus is stable. So, this is not having any affinity for H plus. So, the mobility of H plus is not greatly under control of Cl minus. So, this is having higher mobility, whereas acetic acid, it is a weak acid. What do you mean by weak? It does not like to give H plus. If it does not like to give H plus, acetate ions will be very interested to have H plus with them, means acetate ion is having affinity, liking for H plus. So, this will be definitely attracting H plus. So, the mobility of H plus is less here. So, it is the same H plus, in solution, but here mobility is more, here mobility is less. So, here conductance is more, here conductance is less. Same H plus, but from different sources has different conductances. This is only at this stage of concentration, higher conductance, lesser conductance. But this will not be the situation when you go to infinite dilution. Suppose this HCl, I have gone to infinite dilution. At infinite dilution, I have lot of water between H plus and Cl minus, means plenty of water, almost infinite amount of water is here. Then Cl minus cannot have any control over the H plus. So, the H plus ion is absolutely free in its movement, absolutely free, that is not under control of Cl minus. And similarly, this acetate, so this acetic acid solution, also I am diluting to infinite level. At infinite dilution, there is an infinite amount of water between acetate ions and H plus ions. Earlier, there is some tendency of the acetate ions to control the H plus, because there is a little amount of water between them. whereas now there is an infinite amount of water between and the gap between them is infinite, means one ion is not having any control over the other ion, no intermolecular interactions, all will stop, means this H plus ion is also absolutely free in its migration. Then you see what is the conductance of this H plus ion, what is the conductance of this H plus ion, as absolutely free, in a similar way absolutely free. So, the conductance of this H plus and this H plus will be the same whether it is from a strong acid or it is from a weak acid, no matter. From strong acid the H plus ion's conductivity is the same, even though it is from weak acid also it is the same, but this is possible at infinite dilution. Without infinite dilution the mobilities are different, the conductivities are different. So, at infinite dilution every ion is independent of migration, independent of counter ion. Counter ion is not having any influence. So, this is what 𝗂𝗧𝗪 law says. At infinite dilution, every ion is independent of, every ion has independent migration. That is what the meaning, independent migration, irrespective of the counter ion, that is 𝗂𝗧𝗪 law. So, lambda infinity of HCl is nothing but conductance at infinite dilution of H plus and conductance at infinite dilution of Cl minus. The total conductance of this solution is lambda infinity of H plus and lambda infinity of Cl minus. Similarly, lambda infinity of CH3COO minus, CH3COOH is nothing but lambda infinity of CH3CO minus and lambda infinity of H plus. So, that is what the sum of the individual ionic conductances at infinite dilution is the overall conductance at infinite dilution. But how to find this sum? The acetate ion's conductance at infinite dilution we should find from a strong electrolyte, and H plus ion's conductance also should be found from a strong electrolyte. Summing them up we will get lambda infinity of acetic acid. So, you see what is the application of 𝗂𝗧𝗪 law? I will say now. Lambda infinity of acetic acid, I want to know, that is at infinite dilution what is the conductance of acetic acid, which is nothing but lambda infinity of, I can say CH3COO which is a strong electrolyte, it is a combination of acetate ion and sodium ion, plus lambda infinity of HCl which is a strong electrolyte, a combination of H plus and Cl minus, but actually I want contribution from acetate ion and H plus ion. Acetate ion is here and H plus ion is here, but I want only acetate ion and H plus ion's contribution. So, I want to remove the contribution from sodium ions as well as chloride ions as lambda infinity of NaCl. You see, this is a strong electrolyte, this is also strong electrolyte and this is also strong electrolyte. But for any strong electrolyte we can find lambda infinity by graph, as I said, like this. So, for any strong electrolyte we can find lambda infinity. So, for all these strong electrolytes we can find lambda infinity, and taking the algebraic sum of these two followed by subtraction of NaCl will give you lambda infinity of a weak electrolyte. For any weak electrolyte we can write lambda infinity in terms of strong electrolytes. Lambda infinity of a weak electrolyte like ammonium hydroxide. I want to know what is the lambda infinity of ammonium hydroxide. It is a weak base. So, it is nothing but the contribution from ammonium ions as well as the contribution from OH minus ions. The sum of these two is equivalent or molar conductance at infinite dilution of ammonium hydroxide. We will write this weak electrolyte in terms of 2 or 3 strong electrolytes. Say I want contribution from ammonium ion, so I will take a strong electrolyte of it, say ammonium chloride or ammonium nitrate, let us say ammonium nitrate. Similarly, I want OH minus ions contribution, so I will take a strong electrolyte which is nothing but say sodium hydroxide. I will calculate the lambda infinity of sodium hydroxide at infinite dilution. Similarly, I do not want the contribution from nitrate and sodium ions, because I want only for ammonium ions and OH minus ions. So, I will subtract the lambda infinity of sodium nitrate. So, all these are strong electrolytes. So, adding these two values, subtracting sodium nitrate value, you will get the contribution from ammonium ions and OH minus ions, which is nothing but lambda infinity of ammonium hydroxide. This is how we represent conductance at infinite dilution of a weak electrolyte in terms of strong electrolytes. We will study what is 𝗳𝗏𝗃𝗃 equation. According to 𝗳𝗏𝗃𝗃 equation, the molar conductance of any electrolyte is its molar conductance at infinite dilution minus A root C, that is concentration. A is a constant which is independent of solution. So, lambda is equal to lambda infinity into lambda infinity minus A root C. What this signify? The conductance of any solution is always less than the lambda infinity of it. Means if you take any solution, if the solution is at infinite dilution, it shows maximum conductance. At infinite dilution, the solution will show maximum conductance. At other than infinite dilution, the conductance of that will be definitely less. It is less than its conductance at infinite dilution. So, lambda infinity minus A root C. And as concentration decreases means dilution increases. So, this value keep decreasing, means as dilution increases, the lambda C will gradually become maximum, that is equal to lambda infinity. That is 𝗳𝗏𝗃𝗃 equation. Now, the applications of 𝗂𝗃𝗃 law. One of the important application of 𝗂𝗃𝗃 law is, if you see conductance of any electrolyte at certain concentration and you see what is its conductance at infinite dilution, the ratio of these two will tell you the degree of dissociation. The degree of dissociation of a weak electrolyte, is nothing but its conductance at certain concentration by its conductance at infinite dilution. This value is maximum, this value is moderate, and this is always a fraction. Fraction means less than 1, that speaks the degree of dissociation, and we will do some problems based on this next. Now, let us see the effect of dilution as well as the effect of temperature on conductance, molar conductance, equivalent conductance, specific conductance, mobility, everything we will study now. Suppose first one is effect of dilution. Suppose you are taking, whether it is strong or weak, no matter, I have taken an electrolyte and I am infinite dilution I am doing. So, continuous addition of water makes what? If there is any undissociated electrolyte, that also will dissociate. As a result, number of ions increases, automatically conductance increases. So, as dilution increases, first thing, because of the addition of water, some more electrolyte will dissociate, means its degree of dissociation is increasing. Alpha of weak increasing, alpha of strong also increasing, but the increase in the degree of dissociation of strong electrolyte is less and the increase in the degree of dissociation of weak electrolyte is more. So, both are increasing and is producing more number of ions. Therefore, we get more number of ions, that is number of ions also increases. So, as dilution increases, degree of dissociation increases, automatically number of ions also increases. As the number of ions increases, molar conductance increases. If it is equivalent conductance we are measuring, that also increases, but specific conductance decreases. What is specific conductance? It is the conductance per cc of solution, 1 cc. Suppose you see here, I have 10 A plus, 10 B minus, and I am taking 1 cc of solution, just 1 cc of solution, and here there is one A plus and one B minus, you can say. But when you dilute it, volume increases, but the number of ions does not increase to that extent. So, number of ions per ml is decreasing. Volume is increasing, number of ions also increasing, but the number of ions increase is less. Number of ions is increasing, volume is also increasing, but the increase in volume is more rather than increase in number of ions. Altogether, the number of ions per ml decreases. So, specific conductance decreases. Remaining all are increasing, you should remember, as dilution increases. And because of dilution, the interionic gap, what happens? As dilution increases, interionic distance, due to lot of water between them, interionic distance increases. Interionic distance is increasing means interionic attractions decreases, because distance increases means automatically attractions decreases. If attractions are decreasing, the mobility of each ion is increasing. So, ionic mobility is increasing. Due to ionic mobility increase, there is an increase in molar conductance as well as equivalent conductance, but due to number of ions per ml decreases, specific conductance also decreases. So, this is the effect of dilution over electrolytic conductance. Now, let us study the effect of temperature on electrolytic conductance. Effect of temperature. Suppose I am taking an electrolyte, say A plus and B minus, and there is some undissociated electrolyte also we can take. And now this solution has certain conductance. Now you are heating this, that is what you are raising the temperature. As you are heating means as temperature increases. What happens? Anyhow, any undissociated AB, that will dissociate. As there is a increase in number of ions, the molar conductance also increases. So, as temperature increases, degree of dissociation increases, any undissociated will dissociate, and the number of ions altogether increases, number of ions are increasing. Due to that, the molar conductance increases, because more number of ions means more will be the conductance, and equivalent conductance also increases. And what about specific conductance now? Specific conductance, as we said, it is nothing but conductance of 1 cc of solution, that is 1 cc solution. So, here volume is constant, we are heating, volume is not changing a lot, but the number of ions are increasing. So, here number of ions are increasing and volume is constant, volume of the solution is constant. So, altogether what happens? Number of ions per cc increases. As number of ions per cc increases, specific conductance also increases. Number of ions per cc increases, therefore, specific conductance also increases. One more point, as temperature increases, what happens to intermolecular interactions? The temperature will spoil the attractions. So, intermolecular attractions are decreasing. So, intermolecular gap increases, and at a higher temperature, the mobility of ions also increases. So, altogether conductance increases. So, as temperature increases, interionic attractions decreases, interionic distance increases, and due to increase in temperature, as temperature is increased, ionic mobility also increases. Ionic mobility is increasing, therefore, molar conductance, equivalent conductance, specific conductance, everything will increase with the rise in temperature. Which of the following solutions of KCl has lowest value of equivalent conductance? So, we want to find lowest value of equivalent conductance. You are given 4 different concentrations, and you know the equivalent conductance, how is it dependent on concentration, otherwise dilution. We have learnt as dilution increases, the equivalent conductance or molar conductance both will increase. Due to increase in dilution, interionic distance decreases, interionic attractions decreases, interionic distance increases, so overall conductance increases. So, as dilution increases, equivalent conductance increases. So, we want to have lowest equivalent conductance, means highest concentration we should go for. So, this is one normal KCl has lowest value of equivalent conductance because it is highly concentrated among the given solutions. Let us see one more problem. Which of the following solutions of ammonium nitrate has lowest value of specific conductance? Here it is specific conductance is asked, and that too lowest specific conductance. So, let us see the specific conductance is represented by K, and how does it change with concentration, that is dilution. We know that as dilution increases, molar conductance increases, equivalent conductance increases because the number of ions increases, due to dilution, whereas specific conductance, the number of ions though increases, but the number of ions per ml, decreases. As a result, specific conductance also decreases. So, lowest specific conductance means highest dilution we should go for. Highest dilution means least concentration. Among all these, the least concentration is with second one. So, 0.01 molar ammonium nitrate has lowest value of specific conductance. Now, let us see one more problem. The lambda C means conductance of acetic acid at certain concentration is 20 ohm inverse centimeter square. Equivalent inverse means this is nothing but equivalent conductance of acetic acid. If it is lambda infinity, that is equivalent conductance at infinite dilution of acetic acid is 400 ohm inverse centimeter square per equivalent, then the pH of 0.1 molar acetic acid solution is how much? So, he is asking pH of 0.1 molar acetic acid. You know it is a weak acid. For weak acid, H plus ions concentration, for weak acid, H plus ions concentration is C into alpha. What is C? Its concentration, that is 0.1, and alpha means its degree of dissociation, but you are not given degree of dissociation, you are given conductance at certain concentration followed by conductance at infinite dilution. We know from Коваль-Rosch law, the ratio of conductance at certain concentration to infinite dilution is degree of dissociation. So, lambda C is equal to alpha is equal to lambda C by lambda infinity. What is lambda C? It is 20 ohm inverse centimeter square per equivalent, and what is lambda infinity? That is 400 ohm inverse centimeter square equivalent inverse. Simplification of this, it is 1 by 20, means alpha is 0.05, means this acetic acid is undergoing only 5% dissociation, 0.05 is the alpha. So, therefore, H plus ions concentration of a weak acid is C alpha, that is 0.1 into 0.05, which is nothing but 5 into 10 power minus 3. This is the H plus ions concentration of that acetic acid solution. You are asked to calculate pH. pH, you know, it is a negative logarithm of H plus. So, applying negative logarithm to this, it is 3 minus log 5, and we know the log 5 value is 0.6990. Subtracting that, we will get it as 2.3010. This is the pH, and if you check the pH values given here, second one is the correct answer. Today altogether we learnt what are electrochemical cells and electrolytic cells, electrolytic conductances, and particularly electrolytic conductance you should be careful about units, and the second thing is effect of dilution as well as effect of temperature on electrolytic conductance. These two are most important.